Embedded systems are integrated into our daily lives. For their operation, they need to be reliable and secure. The embedded operating system, Tock, provides those properties. We're going to look at Tock, its components, the tooling it uses to create applications, and then we'll look at a small application running on a virtual system. So let's get started. Controller for traffic signs, watches that can display biometric data, security keys, automotive, and wireless. What do these all have in common? Well, the bumper sticker probably gives it away. But all of these use the Tock operating system, which is built on the Rust programming language. And Rust was chosen because it inherently provides safety features such as memory safety, eliminating large amount of memory bugs, such as buffer overflow, use after free issues, providing also concurrency safety by preventing threads from accessing data that other threads might be writing to at the same time. And then it finally provides traceable, unsafe code. Because, especially in the embedded world, you probably have to have unsafe code. You're going to have to access registers on the embedded processor. And this provides traceability so that you know where the unsafe code is. All of this is provided in a predictable, performant way with a optimized system level language. And that's why Tock chose Rust. On Tock can be the applications that of user processes that drive wireless devices, the security tokens, sensors, and the automotive that had shown previously. And these applications, which are made up of user processes, they also need to have safety. And when running on the embedded device, it's important that a single process in that application can't bring down or compromise the system as a whole. And that's one thing that Tock supports. It supports concurrent, untrusted applications running in that user space and providing the security that the operating system won't fail if the applications do. And this sort of thing makes it ideal for sensor networks, for the Internet of Things, because since the operating system, which is the Rust-based operating system, doesn't require the applications to be written in Rust, those applications can be written in any language, C, C++, and those applications also can be independently updated at times different from when the kernel's updated. And so that's an important feature that allows bug fixes or feature upgrades in those user processes, those applications to occur without the kernel also having to be updated. And this flexibility makes it possible to allow third-party code to run in that application space. So software stacks such as OpenThread, which provides wireless functionality, can run in the user space to be able to have thread connectivity without having to write that stack on in the kernel. And then also other user stacks could possibly use this OpenThread stack, such as Matter, which uses Thread. And I guess in summary, Tock, summarize it in a sentence, that it's an embedded single-threaded operating system that runs concurrent, mutually distrustful applications. And that sentence brings up the question of how is risk reduction performed? Embedded computing systems are often the building blocks of larger final end product systems, and because of that, the schedule of the embedded computing system can directly drive that final product.
Therefore, one of the important risks to keep in mind is being able to develop that embedded system in time so that it doesn't cause upstream delays in the final end product. Also, a lot of times those embedded systems, uh, they are hard to update the code for because it may require the kernel and the application as being compiled together as one unit. So it can be difficult to get that release updated. It can also just be difficult to access the system to update the software on the embedded device. So that's another risk item of development time for the embedded system. And if we look for that roadmap of risk reduction, and we start at the leftmost end with the highest risk. And we look at C-based systems, which are common, and C-based embedded systems using a operating system, which maybe a real-time operating system, that there are the benefits of that is that there's a large support base for a lot of the C-based operating systems, and because of that, there's a lot of developers that work on those. So there's a large developer base to be able to make sure that schedule can be met. There's also a large device base because of the support base and developer base that many devices, embedded devices, support C-based operating systems, or the operating systems that support many devices. But there's risk items associated with this inherent to the language, and is the issue of the buffer overflows, use after free, so those memory issues, concurrency issues with race conditions, and then also just issues with using untrusted dependencies, pulling in code that hasn't been evaluated fully for security risks, or code that was evaluated, but maybe it's been updated and hasn't been reevaluated since it was updated. If we go towards the right of reducing risk and look at switching from C to a memory safe language like Rust, but we look at it without an operating system, so just a bare metal code, maybe with an event loop. Here we gain all the benefits of Rust, so the memory safety, the ownership, the lifetimes, the concurrency safety, and there is a large device base to support bare metal Rust. But there are some risks with that, and those are because it is bare metal and maybe just have that event loop, that it can be difficult to integrate in third-party code into this, and also still may need to use C code for the kernel for interfacing to devices, device drivers, and then also that interface can cause, there can be memory dragons and other issues lurking in there. And finally, there's a dependency on external crates that one may have unforeseen issues with that. If we keep going then further and look at how by using Tock can help out the reduce the risk of the development time and exploitable vulnerabilities. The one part that addressed both is that because Tock is decoupled the application code and the kernel code, they can be updated separately. So that allows for, if there does need to be a patch for exploitable vulnerabilities in application code, that can be done without having to also update the kernel code. And which means that it's easier to release and do that, and then also reduces development time. And another benefit is that those applications can't crash the system, so that there's a safety that you don't get with bare metal. And finally, another big benefit is that there aren't any external dependencies. All the Tock code is in the repository, so you can audit it, don't have to worry about pulling in external dependencies for the kernel and reevaluating when those external dependencies versions change. Now, there is a footnote that if you're using, let's say, ARM, some of the security modules, the trusted platform modules, there might be a reason to pull in external dependencies in the kernel for some of those specific cases. Now, there's risks with everything, and one of the risks with Tock is that one needs to have a no standard library mindset. So heap out, not doing heap allocations, not using standard library API calls. Another one is that Tock isn't real time by default. So that if there are real time embedded problems with, let's say, motor control, that might not be the best solution to use Tock to do that particular part. Perhaps if it's a multi-core processor, one can have the motor control in a different core and then have Tock running in a supervisor role. Now, there have been experiments done with real-time modifications on Tock, but the current code in the repository isn't real-time. So, talked about Tock, but how does it compare with other Rust embedded solutions and other Rust operating systems? The next two slides give details on the Rust embedded landscape, basically at least what I was able to find. First, I would say that I think this is a great site, that this is a source of pretty much most of my information, and it gave me great pointers to go out and start exploring. So I recommend going here first. Now, this slide is on active Rust embedded systems. My next one is on inactive, or what appear to be inactive Rust embedded systems. So the first category is that bare metal category I talked about previously. And here there's some common crates. They're organized a lot of times by the peripherals on the devices, and then the architectural support. And they have board support crates, and then also some agnostic crates to kind of abstract away some of the interface issues so that you can reuse your code on different platforms. The One of the operating systems that's available in Rust for embedded systems is Arial OS. And what's interesting about it is it actually builds upon existing projects in the embedded ecosystem. So these are a couple that are a few that it uses. And particularly, it's using an async framework, Embassy kind of core to it, which is a nice framework because a lot of the embedded systems tend to be I/O constrained as opposed to CPU constrained. So having this as a framework is nice. It focuses really on a lot on networked applications, and it deals with multi-core, which is pretty cool. So this is one system, operating system to look at. Another one is Hubris, which is maintained by Oxide Computer. And just as a side note, they have a really cool podcast. I've learned a lot. They do deep dives into different Rust issues, and it's really, I think, really well done. Their system, I haven't used it, but it's a message passing kernel. It's really lightweight because it's meant to run on their motherboards for their server business, and not really be in the way of things. And so it's an interesting code to look at for a developed system. Now, one of the systems, if we go to the next page, so these don't appear to be actively developed. One is called Drone OS, and its last commit was in 2022. It was interesting because it uses dynamic memory, and it has fully preemptive multitasking, which is interesting. Another one was a Google project that was called Cantrip OS, and it was a microkernel-based, Rust-based operating system, but it was actually archived in beginning of 2024. So there haven't been new commits, and I haven't seen a actively maintained fork of either of these two yet. This is now we looked at the ecosystem of, of the Rust-based ecosystem and other operating systems. So time to turn back to Tock and start looking at some of the details of the Tock operating system. Here we have a block diagram of the Tock system, and the system can be divided into two parts, which is shown here with the dotted line of either the Tock operating system below the line or the processes, the user applications that use the Tock operating system to run, which is above the dotted line. You can see applications can be written in a variety of languages. Here show application written in C, an application written in Rust. The choice is the user that's using the Tock operating system. Besides applications which may be doing specific things, interacting with a user or interacting with other systems, there's also services, and services are user processes, but they provide a service to other user processes. So, for example, the 802.15.4 thread stack, wireless stack, could be a service in this untrusted space. And that's one of the properties that all of these processes share is that the operating system considers them untrusted. So they don't have direct access to the data structures in the kernel. And this untrustedness is enforced with memory management protection units so that that these don't have their own unique address space, like let's say a Linux environment, but they all share a space that is different from the kernel, so they're untrusted. Another part that's of this system that's untrusted is below the dotted line, so in the kernel, in the operating system area, and that's capsules. These capsules you thought of as it's kind of like drivers that interface to user applications or services. And this interface is done through syscalls, which is a standardized definition API of how these applications and services can interface below in this kernel layer. The capsule is also untrusted, but it's different. That security is maintained differently than the processes, which are in their own memory space. The capsule shares the same memory space as the kernel, but the untrustedness is enforced at the compiler level with the traits and other um, types that Rust provides. So here, the trust security is provided by the compiler, and here it's provided by a memory protection unit. With the other pieces in the Tock operating system are the kernel, and then how the kernel interfaces to the hardware, which is with drivers. This all of this code is considered trusted. So this code has access to, the drivers have access to all of the data structures of the kernel, and it can operate in unsafe mode. So kernel code can operate in unsafe mode. The driver code can. Generally, capsule code cannot. But the driver code needs to be able to do that to interface with the hardware, where a lot of the peripherals, timers, analog to digital converters, things like that are. And the hardware for actually running the Tock operating system can be either a ARM processor, Cortex-M, something with a memory protection unit, or RISC-V processors, also with memory protection unit. You can technically run it without a memory protection unit, but then you lose this security between the untrusted here and with the kernel, so that you can, because this code up here can also run unsafe things. So now, without a memory protection unit, you could have issues where the application could crash the operating system. And the operating system is single threaded. So there's a single thread event loop that runs the kernel code, that runs the capsule code, and that can then preempt the applications and service at this untrusted user level. So there's different. The scheduler in here decides whether this is preemptible. I was referring, if look at the bullet here, that the round robin schedule runs untrusted user processes, and it runs them in a preemptible mode that they can just be interrupted in what they're doing. There's other schedulers that can be used with the kernel that doesn't do that. Some of the other features are that the kernel doesn't have a heap, so that you don't have dynamic memory allocation. It all has to be set up with compiling. Capsules also don't have a heap, so the way they get memory is a really interesting way through the processes, which is we'll talk about later. Also, the capsules, since they're part of the single thread event loop, they're non-preemptible, which means that the capsules could basically halt the kernel by just sitting there and not doing anything. So that's something to keep in mind with when writing capsules or working with those. A couple other points I mentioned before, that it's important to have a no standard library Rust mindset, so not using heap allocators. Also having a mindset of asynchronous programming concepts. In this case, a lot of it's with callback functions. And this is important because a lot of embedded systems problems are ones of I/O input-output constraint and not CPU bounding. And that these applications can be compiled separately from the kernel, which allows better management because these can be loaded onto an existing kernel and updated that way. And that finally the processor, the trustfulness is maintained, or untrustfulness, by using a memory space that's separate from the kernel. So talked a lot about the Tock system. Now, how do you actually develop for the Tock system? The tools for the Tock development ecosystem can pretty much be found on Tock's GitHub. So there's the kernel repository, which is Tock, and then there's application examples. So there's C application examples, which is their libtoc-C repository, and there's also Rust application examples, which is their libtoc-RS repository. And so these examples also have different API to help make development easier for applications. One of the differences between the two is the compiler tools that need to be installed. So libtoc-C uses GCC, and libtoc-RS uses LLVM. And one of the side effects of LLVM, at least used to be, was the code here is not as easy to relocate in memory as with GCC. And we'll talk more about that at in a later slides in a different talk. But so these are the repositories. So building the kernel, the instructions there, and building the applications. Now, how do you get all of the code onto the board? Well, that's through Tock Loader. And so there's a repository for Tock Loader, or it's a Python tool that you can pip install too. And what you can use that for is to be able to interfaces with a USB tool to be able to transfer a bootloader to get the code onto the board, either with Seger's J-Link or the open source OpenOCD, OCD, which TockLoader can use either of those. So the basic idea is compiling the code on a development system such as Linux or Windows, and then using TockLoader to take that compiled cross-compiled code for and put that as on the board, and then use that also for getting the applications on the board. Now, when it comes to debugging, there are several options. One is using TockLoader's listen, which allows when you're running the kernel and running the applications on there, not only can you use TockLoader to load applications, erase applications, but then also you can talk through, there's a console that you can talk with the kernel for starting and stopping processes, these user processes, and also getting through the serial interface with the listen, getting print statements. If need to be able to do more interactive debugging, can also use GDB's toolchain to connect to the applications or kernel and debug that way. So, in summary, what we've talked about is just like a few bullets to squash everything down into a few bullets. Is that the the whole point with Tock's embedded operating system? It's written in Rust for the safety and reliability. Some key points in it. That's a single-threaded kernel. It does cooperative scheduling. It's event-driven. It's not a hard real-time OS, and it prioritizes safety over the strict timing of a real-time OS. It can run concurrent untrusted applications on microcontrollers safely so that the applications can't take down the operating system or other applications. And it isolates those. You need to have memory protection, hardware memory protection, such as with the ARM and RISC-V hardware platforms that have that to be able to take advantage of that ability for that safety. And then it also decouples the application and kernel development for flexibility.